Hello, Pre-Calc. We're taking some notes on the second section about limits. We're going to talk about some important trig limits and some limits at infinity. So the first is we've got to go through these three trig limits that will always be true. The first is the limit as x approaches 0 of sine of x over x is equal to 1. If you think about what we know, if I were to plug in 0, I would get sine of 0, which is 0 over 0, and I know that that's a problem where we'd have to do more work, but I am simply telling you this is a limit to be memorized. Another is the limit as x approaches 0 of 1 minus cosine of x all over x. And this one, again, if we were to plug in 0 and 0, we'd get 0 over 0, which is a problem. But this limit goes to 0. And then last but not least, we have one with tangent. The limit as x approaches 0 of tangent of x all over x is equal to 1. These three would be three limits that you should pretty much just know and memorize. The only thing to note is that if this thing inside the inside cosine, sine, or tangent is the same as what's in the denominator, this is also true. So for example, if I had the limit as x approaches 0 of sine of 4x over 4x, well, these two things are the same, and so this limit is still just 1, like we said above. I'm going to show you the next slide, and if you would like to pause the video and write these three down, we'll be doing these three in class together. So take a moment to write these down, and we've got a couple more for you. Again, I would ask you to pause the video and write these down in your notebook. Most of them will be relatively quick examples, so there will not be a lot of need for space in your notebook for most of these. Let's talk about limits at infinity. What happens as x gets really, really big or really, really small? Well, let's consider this function for a second. F of x is equal to 4x to the fourth minus 3x squared plus 2x. What do we know about this curve? Well, hopefully you remember we had our leading coefficient test, which says we're going to look at the term with the highest degree. And in this case, it's even, so both ends are either going to point up or down. And because our leading coefficient is positive, I know both of my ends are going to point up. I don't necessarily know what's going on inside, but the end behavior will look like that. So we could say the limit as x approaches infinity of this function, well, consider the thing we just drew. As x is getting really, really big in the positive direction, so is my y. This is equal to infinity, and we say, therefore, it does not exist. This little 3 symbol means, therefore, why does it not exist? Well, infinity is not a number. I can't actually be infinity. So we don't say that I get to infinity, because infinity is an idea, not a number. We could also say the limit as x approaches negative infinity of this function. Well, it's the same thing. We're going to look at this graph. As x is getting really, really, really small over here, what's happening to my y? Well, it's getting really, really big. So it's approaching positive infinity, and again, we would say, therefore, does not exist. These would be the solutions to those limits for this problem. In general, we are going to use either the leading coefficient test to determine end behavior, or we're going to consider our horizontal asymptotes. Our leading coefficient test or horizontal asymptotes with end behavior. So let's talk about some limits involving infinity, known as principles of dominance. Let's start with this one. The limit as x approaches infinity of some x to the a power over x to the b power, and a is less than b. So this is a rational function, right? Is a rational function. And as I mentioned above, we might want to consider our horizontal asymptotes. So think back, or maybe even flip back, when I had a polynomial in the numerator that had a lower degree than the denominator, where did we have a horizontal asymptote? An example of this would be y is equal to 1 over x. The numerator degree is 0, the denominator degree is 1, 0 is less than 1. Where does this function have asymptotes? Hopefully you remember. This is what this looks like, and we've got a horizontal asymptote at the line y equals 0. This is always going to be true, thus this limit will always be 0. If the numerator has a smaller degree than our denominator, the limit as x approaches infinity or negative infinity will be 0. What about a different case? What if we have some rational function again, where the numerator and denominator have the same degree? A is equal to b. Well, once again, we think back to hopefully what we remember about horizontal asymptotes, and in this case, the horizontal asymptote is at the leading coefficient of our numerator divided by the leading coefficient of our denominator. That means our limit is going to be equal to whatever these coefficients are. In this case, we'd say c over d, but of course it depends on the problem that we're actually looking at. And then last but not least, what if our numerator has a greater degree than our denominator? In this was the case where we either had a slant asymptote or, well, we definitely had no horizontal asymptote. Maybe I should write that first. This was the case where there was no horizontal asymptote, and sometimes we had a slant, right? And how did we decide on the slant? Well, we would do the division that we were given in the problem. We would take the numerator and divide it by the denominator. And once we do that, we are going to consider the leading coefficients. So in this case, our limit will either be positive or negative infinity, and that again is of course then does not exist. And how do I know if it's positive or negative infinity? Well, this will be determined by that leading coefficient. So let me give you a brief example in this video, and then we'll look at a couple more examples together. If I had f of x is equal to, let's say, 5x to the fourth plus 3x all over negative x squared plus 1. Well, I look at this and I see that my numerator has a greater degree than my denominator, right? 4 is greater than 2. So I'm going to do the division, and I really only need to focus on the leading coefficients. So I'm going to take 5x to the fourth over negative x squared, and I go ahead and do that division, and I would get negative 5x squared. Well, what does the leading coefficient test tell me for negative 5x squared? I would have 2 sides pointing down. Thus, the limit as x approaches infinity of this function will be negative infinity. As x approaches, x approaches positive infinity, y is approaching negative infinity, and the limit as x approaches negative infinity of this same function would also be negative infinity, and in both cases, we would really say the limit does not exist. Another way, maybe I'll do that example in class. So let's take a moment to, if you would like to pause the video and write down these 3. So we've got 3 examples. Pause the video, write them down. And we've got one more down here. Again, you might have to pause the video and write this down. We will do all of these in class together, and then you'll have some work time on limits at infinity. I hope you have a lovely rest of your day.